Module 13.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 13.2. What are common hypothesis tests for categorical data? Previously, we looked at the fundamentals of hypothesis testing. In this section, we will look at common hypothesis tests for categorical data. For each type, we will go through the steps. It's important to note that all of the steps are necessary for the analysis, but usually only the end result is reported. It's also important to note here that we're only going to be looking at a small selection of hypothesis tests for categorical data. There are many, many more that are available. One sample proportion z-test. You will want to start by determining what you would like to prove about the population proportion. Usually, you will be comparing the population proportion to a known value. Going through the basic steps to conduct this test, you'll begin by stating the null and alternative hypothesis. Next, you need to check that the necessary assumptions are met. You'll notice that these assumptions are very similar to the assumptions that we saw for the central limit theorem, with some minor adjustments. For the results of the hypothesis test to be valid, we do need to meet these necessary assumptions. For the one sample proportion z-test, we need to confirm that the sample size requirements for the central limit theorem are satisfied and that the sample is randomly selected. For a single proportion, we need to check the following sample size requirements. N times p naught is greater than or equal to 10, and n times 1 minus p naught is greater than or equal to 10. This is the same as having the expected count of at least 10 in each category, assuming that the null hypothesis is true. Notice the difference here compared to what we've seen before is p naught is going to be the value under the null hypothesis. The symbol p naught is the value listed in the null and alternative. Other resources may use slightly different sample size requirements. Next, you'll calculate the appropriate test statistic. The formula is given to you here for completeness, but we will not do these by hand. Next, you'll use software to help you find the p-value. And then finally, we'll state our conclusion in context. Let's look at an example. A commercial claims that 9 out of 10 dentists recommend a brand of whitening toothpaste. We will test the claim that the commercial is wrong unless the 9 out of 10 dentists recommend a particular brand of whitening toothpaste. A random sample of 100 dentists is obtained. Of these 100 dentists, 82 indicate that they recommend the toothpaste. And we're going to use alpha is equal to 0.05. Notice that although the sample proportion, p hat is equal to 0.82, is less than the 0.9, we cannot use this information alone to claim the commercial is incorrect. The sample proportion, p hat equal to 0.82, may be specific to this sample of 100 dentists, so we need to perform a hypothesis test. The first thing we do is we set up our hypotheses. Under the null, we assume that the population proportion is equal to the 90%. Under the alternative, we're going to try to prove that the population proportion is less than 90. Next, we need to check the necessary assumptions. The sample was random, and if we check the sample size times the hypothesized proportion of 0.9 and the sample size times 1 minus the hypothesized proportion, we find that both of these values are at least 10, so the sample size requirements are met. Since the assumptions are met, it's valid to perform the one sample proportion z-test. Next, we use software to calculate the statistic. We find the p-value, which will also be given by software. And in conclusion, we find that at the 5% significance level, we have enough evidence to conclude that the proportion of dentists who recommend the toothpaste is less than 90%. One thing to note here in terms of the test statistic is some softwares will report a chi-squared test statistic instead of the z, but a z-squared is the same thing as a chi-squared. I'll talk more about this in the videos where we look at how to calculate these using SAS and R. Next, we're going to look at the one sample proportion binomial exact test. If the sample size requirements for the one sample proportion z-test are not met, we cannot assume that the sampling distribution is normal, and we must use a binomial distribution. In cases like this, we need to use what's called an exact method. You want to start by determining what you would like to prove about the population proportion. Usually, you will be comparing the population proportion to a known value. Let's look at an example similar to the previous one with some minor changes. A commercial claims that 9 out of 10 dentists recommend a brand of whitening toothpaste. We will test the claim that the commercial is wrong unless the 9 out of 10 dentists recommend the particular brand. A random sample of 20 dentists is obtained. Of these 20 dentists, 17 indicate they recommend the toothpaste. Use alpha equal to 0.05. Although the sample proportion p hat equal to 0.85 is less than 0.9, we cannot use this information alone to claim the commercial is incorrect. The sample proportion, p hat equal to 0.85, may be specific to this sample of 20 dentists, so we need to perform a hypothesis test. Notice here our hypotheses are the same as they were before, but now for the exact test, we do not need the assumption about the sample size. Again, to find the p-value, we're going to use software, and in this particular case, the p-value was 0.3231. So our conclusion in this case is going to be at the 5% significance level, we do not have evidence to conclude that the proportion of dentists who recommend the toothpaste is less than 90%. In general, when working with hypothesis tests, if one of the assumptions are violated, there is usually an alternative test that does not require that assumption. The problem with the alternative test is they sometimes may not be as powerful. Next, we'll look at the large sample hypothesis test for two population proportions using independent samples. So you want to start by determining what you would like to prove about the difference between the two population proportions. Next, you'll state your null and alternative hypothesis. And to check these assumptions, our sample size requirement will now be based on the two different sample proportions and whether or not we have expected counts of at least 5 in each category. Other resources may use slightly different sample size requirements. Next, you can calculate the test statistic. The formula here is given for completeness, but we will be using software. You'll find the p-value and state the conclusion. For example, Time magazine reported the results of a telephone poll of 800 randomly selected adult Americans. The question posed of the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for health care reform? The results of the survey are given here. The question is there sufficient evidence at the alpha equal 0.05 level to conclude that the two populations, smokers and non-smokers, differ with respect to their opinions? Although the difference between the proportions, which in this case p hat non-smokers minus p hat smokers is equal to 0.37, differs from 0, we cannot use this information alone to claim that the populations differ. The sample information may be specific to these two samples, so we need to perform a hypothesis test. The first thing we do is set up our hypotheses. Under the null hypothesis, we assume that the two proportion or population proportions are equal to one another, and on the alternative, we're going to try to prove that they differ from one another. Next, we need to check our assumptions. Of the non-smokers, 351 said yes, and 254 said no. Of the smokers, 41 said yes, and 151 said no. Notice here that all counts are greater than 5. There is a mistake here in the slide, that 10 should be a 5. And the sample was random, so the assumptions are satisfied. Further, there is no reason to suspect that the samples are not independent of one another. Using software, we can calculate our test statistic and get our p-value. For this particular example, the p-value is close to 0. So at the 5% significance level, we have enough evidence to conclude that the proportion of smokers who agree with the tax differs from the proportion of non-smokers who agree with the tax. Chi-square test for independence of two dichotomous variables. For the large sample test for two population proportions, we want to prove that the two population proportions differ from one another. Notice that we have two variables, the variable that defined the populations and the variable inspected within each population. If the two population proportions are equal, we can say that the two variables are independent of one another. Independence means that the distribution of one variable does not depend on the other. Recall, we can summarize two variables in a contingency table. In this scenario, we will have a 2x2 contingency table. Looking at the basic steps, we start by stating the null and alternative hypothesis. These null and alternative hypotheses look slightly different than what we've seen before. The null will still be listed first and state that the two variables are independent, whereas the alternative will state that the two variables are dependent or not independent. For our assumptions, for the results of the hypothesis test to be valid, we need to meet the necessary assumptions. For the chi-square test of independence for two dichotomous variables, we need to confirm that the sample is random, the expected cell counts are all 1 or greater, and at most 20% of the expected counts are less than 5. The expected cell counts are what we would expect to see in the sample if the variables of interest are indeed independent. Other resources may use slightly different sample size requirements. Again, we could calculate the appropriate test statistic. The formula is given here for completeness. We'll find the p-value and state our conclusion in context. Let's look at our example again. Time magazine reported the result of a telephone poll of 800 randomly selected adult Americans. The question posed of the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for health care reform? The results of the survey are given here. Is there sufficient evidence at the alpha equals 0.05 level to conclude that a person's opinion is independent of smoking status? So notice here our hypothesis or our question of interest is slightly different than how we posed it before. Therefore, our hypothesis test will now change. First, we set up our hypotheses. Under the null, smoking and voting status are independent, and under the alternative, they are dependent, or we could say not independent. To check our assumptions, we can create a contingency table based off of the information given from the survey. Notice where these values come from. Looking at the non-smoker row, we know that we had 605 total and 351 yeses. Therefore, to get the non-smoker no's, we took the 605 minus the 351. For the smokers, to get the no, we take the 195 minus the 41. We check the assumptions by looking at the expected cell counts. Statistical software will give this to us. For this example, here are the expected cell counts. For the chi-square test of independence for two dichotomous variables, we need to confirm that the sample is random, which was given. The expected cell counts are all 1 or greater. Here, every expected cell counts is greater than 1. And at most, 20% of the expected cell counts are less than 5. For this example, none of the expected cell counts are less than 5, so we've met that assumption as well. Using software, we can find the appropriate test statistic and p-value. For this example, the p-value is close to 0, so we can say at the 5% significance level, we have enough evidence to conclude that a person's opinion and smoking status are dependent or not independent. So notice here that our research question drives which hypothesis test we are going to perform. Chi-square test of independence for two nominal variables. Chi-square tests are not restricted to dichotomous variables. We can also test to see if there is evidence against two nominal variables being independent, where one variable has R levels and the other has C. Recall, we can summarize two variables in a contingency table. Notice here the null and alternative hypothesis are the same as that of the chi-square test with two dichotomous variables. Our assumptions are also the same. Given here's the formula for the test statistic, as well as how to find the p-value, and then to finish we always state our conclusion in context. Let's look at an example. A group of students were classified in terms of personality, introvert or extrovert, and in terms of color preference, red, yellow, green, or blue, with the purpose of seeing whether there is an association or relationship between personality and color preference. Notice that the color and personality are both nominal variables. Data was collected from 400 random students and given in this table. Our question is there sufficient evidence at the alpha equals 0.05 level to conclude that a person's personality is independent of color preference? We need to perform a hypothesis test. Setting up our hypotheses, under the null hypothesis, we assume that personality and color preference are independent, whereas in the alternative, personality and color preference are dependent or not independent. We need to perform a hypothesis test to prove this. So as usual, we check our assumptions. Given here are the expected cell counts that were found using technology or statistical software. And so notice for the chi-square test of independence for two nominal variables, we need to confirm that the sample is random, which we were given. The expected cell counts are all 1 or greater, and in this case all values are 1 or greater, and at most 20% are less than 5. So again, none of them are less than 5, so we have met that condition. We could also calculate our test statistic, which in this case is 71.2, which gives us a p-value close to 0. So again, at the 5% significance level, we have enough evidence to conclude that a person's personality and color preference are associated. When working with ordinal variables, we can investigate a general association using the chi-square test for independence we saw previously. Alternatively, we can investigate more than a general association between the variables. Recall that the ordinal variables have an order or a ranking. To take this characteristic into account, a score can be assigned to each level of the variable and a mean taken. The test associated with a nominal and ordinal variable is known as a row mean score test. Recall that we can summarize two variables in a contingency table where the ordinal variable is summarized in the rows. Given in the scripts are the basic steps for conducting the row mean score test. And then finally, a hypothesis test for two ordinal variables, also known as a linear bilinear test. When working with two ordinal variables, we can investigate the general association using the chi-square test for independence or a difference in rows, both of which we just saw. Recall that ordinal variables have an order or ranking. To take this characteristic into account, a score can be assigned to each level of the variables, and we can test for a non-zero correlation between the scores. Given in the video script are the basic steps for conducting the linear bilinear test. For both the row mean score test and the linear bilinear, we have not looked at examples. These are both included just for your general knowledge. This concludes the Module 13.2 notes.